tecnologías de antenas para sistemas de comunicaciones sin OC, realizada por Vedar Prabhu Basavarajapa. A continuación, Vicent, que es el secretario del tribunal, os va a leer la normativa.
La defensa de la tesis consistirá en la exposición por el doctorando de la labor realizada, la metodología, el contenido y las conclusiones, con una especial mención a sus aportaciones originales. Los miembros del tribunal formularán al doctorando cuantas preguntas estimen oportunas. Los doctores presentes en el acto público podrán formular preguntas en el momento y forma que señale el presidente del tribunal. Finalizada la defensa y discusión de la tesis, cada miembro del tribunal formulará por escrito una valoración sobre ella, así como sobre las actividades de formación realizadas por el doctorando. El tribunal emitirá un informe y la calificación global en términos de no apto, aprobado, notable o sobresaliente.
You can start with the presentation.
Okay, thank you so much. Thank you. A very good morning, members of the tribunal, Professor Vincent, Professor Bella, Professor Susana. Good morning, Professor José Bastarisha, my advisor, and everyone in the audience, TTI colleagues, Cantabria, everyone. It's a delight to have you all here at my defense. So welcome everyone. So this is the topic of my doctoral defense, a proposal of antenna topologies for 5G communication systems. Let me share with you the outline at the outset. What I will do is I'll tell you why do we need 5G antennas at all. There are already antennas for 4G and LTE. Why do we need different kind of antennas for 5G? So first I'll take that question out. So I'll make that clear and then talk about the requirements for 5G antennas and what are the challenges in addressing the problems that come up with this. Then talk to you about the state of the art. Then tell you about the 3 solutions that I propose towards realizing those 5G antennas, namely the quasi-optic end-fire element and the quasi-optic end-fire element and the massive MIMO and single RF antenna array and the millimeter wave antenna. Then conclude and then share with you the research dissemination activities that I have been involved with and then tell you about the future work that I think can be extended to this proposition. So basically, there is a need for 5G antennas. Why do you think 5G antennas are necessary at all? According to the cellular traffic predictions of Cisco, 5G requires a complete re-architecting of the device to be deployed. That is, you cannot use what is already existent in 4G and LTE systems into 5G antennas or 5G devices. You need to completely make a complete revamp of the entire infrastructure. That's a fundamental requirement. The other thing is that the design conceptualization and validation of these antennas is completely non-existent in the previous generations. So you need to make a complete new approach. So what I do is I try to take you through quickly a summary of how the 5G requirements and the 4G and before differ from these two. So the first requirement is frequency of operation. As you can see, these are the frequencies of operation for 4G. For 5G, it's TV white space, 3.5 GHz and greater than 10 GHz wideband. So considerable difference between the frequencies. For beam pattern in 4G and before, it's sectoral and omnidirectional required, and for 5G, it is usually highly directional. And the number of beams are single or dual for 4G and multiple beam for 5G. And reconfigurability for 4G generally, because there is no reconfigurability at all. I mean, you set the base station, you put it into the base station, and you run it for years. You maintain the base station power station, but you don't look at the antennas at all. It's like it's fixed there. But in 5G, it's an integral part. You have to have reconfigurability in the 5G scenario. It has to change dynamically. And in type of cell deployment, there are multiple number of cells, macro cells, small pico, and femto cells. For macro cells, this is what you see in 4G. They are large, big cells on the cellular base station towers and surrounding the base station towers. And the small pico and femto cells are for the 5G, which are much smaller in size. So as we move towards 5G, we are seeing more densification of the networks. Gain of antennas is moderate, that is 10 to 12 dBi, and this is for 4G, and for high gain of 20 dBi for 5G. Form factor is generally large. 4G and before, the spatial footprint is not an important criteria, but for 5G, it's very important that for millimeter wave you have a small form factor. The power handling capability is moderate for 4G and before, and for 5G it is very high. Because especially for massive MIMO purposes, when you have large number of antennas, large amount of power that is there, so you have to have a high power and handling capability. The scanning plane is generally azimuthal scan for 4G and before, and for 5G it is azimuth and elevation scan. Tilt plane, elevation tilt is required in 4G and before, but for 5G this becomes largely redundant because you have an elevation scan already in the 5G antennas. You don't just do the tilt, but you can also scan along the tilt. So that's the advantage of having, that's the requirement of having 5G antennas. What is the requirement according to the standardization bodies? 3GPP and ETSI. They have proposed three. I'll take out of the document. I have taken three important characteristics. What is the condition on beam state, on the base station beam patterns, on the receiver beam patterns, and on the beam switching time? The base station beam patterns for 5G, the patterns are completely dynamic, so they keep changing with time. It just moves around, and so it's very difficult to assess considering the multi-path, it is difficult to assess the pattern of the antennas. So what they have come up with is a solution, novel solution, very good solution, which says we will just characterize in-cell and out-of-cell radiation. So that is an assessment parameter, this in-cell and out-of-cell radiation. Then receiver beam patterns for CPE should have a gain of 5 dBi, but that is for customer premises equipment should have a gain of 5 dBi, 9 degree half-power beam width, and lambda by 2 link element spacing for the receiver side of the mobiles. And then the most important concept, beam switching time for base station antennas. When you talk about 5G, the most important parameter proposed in all of the documents that you come across is they want to decrease the latency. So to decrease the latency, the beam switching time should be less. And this can be done according to this rule. That is, the beam switching time should be lesser than the cyclic prefix length. That is, if you are using OFDM in LTE or in other 4G networks, the cyclic prefix is just the guard band is there between two symbols. So this cyclic prefix length that is there between the two symbols should accommodate the beam switching time. That is, the beam switching time cannot be more than this guard band time. If it is, then there is an overlap, intersymbol interference, delay, all of those stuff. So these are the three requirements set up by the 3GPP and the ETSI standards out there. And these are the two references I keep here. It's for those documents. Okay, so what am I addressing? This is the background. This is the background I just discussed with you. What am I addressing? The problem description, the technology, the massive MIMO, single RF MIMO, and millimeter wave, three technologies. And the problems. In massive MIMO, the problem is, as the name suggests, it's massive. So there are more than 64 number of antennas. So it becomes very difficult to implement such a scenario given all the antenna considerations that go into this. And single RF MIMO, it's completely on the other direction. That is, it wants to reduce the number of RF chains. So it's challenging. And the millimeter wave, it wants to have a high path loss at millimeter wave frequencies and uses a multi-path as an advantage to that. So both the things have to be realized. So each of these problems has its own challenges that need to be addressed. For massive MIMO, multiple beam has to be realized, multiple beam steering has to be realized, enhanced spectral efficiency has to be done, enhanced per user throughput has to be given. For single RF, multi-antenna and multi-beam with either, if you don't reduce the number of RF chains, at least have a few number of RF chains or single RF chain, and then adapt them to spatial and index modulation, and also give high reconfigurability. Millimeter wave, okay. What happens at 28 GHz or let's say if you go higher frequencies, the path loss increases tremendously. It's a well-known fact. So what do you need? You need high directive beams which should be operated in multiple beam scenario as well, and they should be having a high power handling capability. So these are the challenges. These are the problems. So over the next 40-50 minutes, I will try to address this and share with you how I try to work over this. But before I go, I have to give credit to all the work that was done before. So this is what was done. This is massive MIMO setup from Argos, Lund, Samsung, these three. And this is single RF MIMO setup. This is a low power CMOS switch, and this is the low power CMOS switch. This is switches with printed configuration. So these were the ones that were existent that time, the prominent ones at least. And millimeter wave was well researched when I started off, and it was like there are a lot of number of antennas that are present here. It's all tilted Kumler antenna, then you have a torso antenna, you have planar patch antenna, differential feed antenna, increased cross polarized discrimination antenna, printed Yagi antenna. So all of these basically had the main goal is to increase the gain. The gain was to increase the gain of the antenna and to operate at millimeter wave frequency. This is another kind of antenna which is a lens antenna, which is a transmission line fed. The transmission line length controls the phases and therefore makes the high gain. And this is the other kind of antenna. This is something on which my work is also mostly based on, in which you feed. I'll come to this in detail. So these are the three different state of the arts. Okay. In this slide, I try to capture all the things that I'm going to say next in a and put them in a block diagram. So 5G, it requires this technology, massive MIMO, and it requires multi-user, multi-beam. The solution was this antenna that you see here. And for single RF, the requirement is to reduce the number of RF chains to lower the power, and that is this one. And then for millimeter wave, you have high gain beams and you have this antenna. This is just a snapshot trying to summarize all what I'm going to say next in this flowchart. Okay. Now I'll go one by one into each of those three antenna elements. Now, quasi-optic end-fire antenna element. The most important aspect in any kind of antenna array design is the antenna element. If you don't get the antenna element right, the array may not function as wanted. So basically, the initial efforts were put into this, and in coming up with a concept which clearly which gives a higher gain for individual element. So the focus was that if the individual element has a higher gain, then the array can naturally be higher. So for that purpose, the gain of the individual element was made higher. It was around 6 dBi. The antenna design that you see here is a printed configuration, which is printed on the front and on the back. There's a substrate here, and it has a reflector, a dipole, and parasitics that are coupled onto this driver dipole. And then there is a novel arrangement of the parasitics on the antenna, which aid in the gain enhancement. What is the mechanism that is used to make the gain enhancement? Well, you might be familiar with the optical fiber cable. So in the optical fiber cable, what happens is the core has the highest refractive index and the cladding has the lower refractive index. So if the rays go outwards from the core, outwards towards the periphery, then due to total internal reflection, the rays bend backwards into the same core. So that enhances the gain completely. So this is something like that. This is analogous to that, but the difference is that the refractive index is controlled by the way in which the parasitics are placed on the antenna element. So what I do here is exactly what I do here is, if you start starting from the center, from this portion, the refractive index is very high here, and as you move outwards, the refractive index decreases. This you can see here. How do you get this refractive index? You extract this from S parameters by feeding port 1 and port 2 and take this S parameters to calculate the refractive index out of this, and then plot it, and so you have dependence which actually decreases as you move outwards. So essentially, this all effectively becomes something like optic fiber cable, that it has a high refractive index, it decreases outwards. And then this gives, this is the antenna, actual antenna dimensions of the antenna, backside, the surface current distribution, the fabricated prototype, this is the measurement of the pattern, and this is the return loss, simulated, measured, compared. So there's a good agreement between simulation and measurement. There are some things which need to be addressed in the pattern squint, which has been addressed in the thesis. I've explained how the squints were corrected, or methods to correct the squint. That basically arises from the asymmetry in the current distribution. But overall, this was a good antenna element array. Next, okay, the antenna element array was designed. The next approach was to make the massive MIMO antenna array. The approach that is followed here is that there is no scanning that is done. We don't scan the beam. We just switch the beam from direction to direction. So And the method I propose here is that you use a single block of two elements as a building block, as a Lego brick you might say, to realize any number of beams in any direction. When I say any, I will come to how limited or how not limited they are later. But you can essentially realize multiple directional beams using this simple block of two elements. How do you realize this two element block? I call this the building block of the design. So you have a single element here which is fed at 0 degree, another one fed at 180 degree. They are both fed at equal amplitudes. Now this gives you a beam like this, which has a cancellation null in the center. So there are two beams actually. This is an odd symmetrical phase excitation, and this when you do a kind of change to the spacing between these elements, you can see the null is still there. It is still pronounced in the same direction, in the center. So this gives us an advantage to use it as a non-line of sight application. That is, the null does not move. And you have, but these beams can be moved by the spacing, changing the spacing of the antenna element. So basically, what I'm saying is that if you look at this design, as you put a vector right here, this way, then the beam is coming out of the board like this. So you control the beams using that vector. You can change the vector. You change the way you feed the beams, the phases you feed in the beams. You change the vector in which you change the direction in which the beams are pointing. So this is the basic concept on which the massive MIMO antenna array is. This one is based. Okay. Now I said massive MIMO was 64 antennas, but for practical purposes, I have made 16 antennas, 4 by 4. So for assessment, 4 by 4 assessment is enough to say for the 6 by 6 because the scheme I say here is extendable, is scalable to the 64 antenna concept as well. So I will show that here. Here what I do is I am showing the scalability of the concept. Here it is 3 by 3 antenna array. As you can see, there are 3 by 3 antenna elements. And you have 3 excitations which are +1, and this gives the classical bore side beam, as you know. So you feed all of them with 1 and 0 phase, a beam comes out of the screen like that. So that's what it is. And then you do it this way, that is, you feed these two with 180 degree and these two with 0 degree, and you do and match terminate the other ones. Then you have this kind of a beam which is horizontally aligned. You see, so the vectors are like this. The vector is coming out like this. So the beams are also in this fashion, horizontally aligned. And this you can extend it to other stuff vertical. You can make it vertical in the same way, or you could have quadrigonal pattern completely. And this can be tilted, slant beam, and another slant beam of 45, minus 45, plus 45 as well. And this is just the slant beam. It's not the polarization. It's just the beam is slant here. Okay, so this is what I take you through. Basically, the thing is, if you go 3 by 3, the general trend in the massive MIMO scenario is to have 64 and 128 antennas, as you already know. So it's like to have even number of antenna elements and therefore have even number of subarrays as well. So if you do it 3 by 3, you cannot possibly do a proper extension to the and a complete justification to the entire array. You will have some elements which are not fed. So for that purpose, what I propose here is a 4 by 4 antenna element, a subarray, using the same scheme, using such a kind of excitation matrix. That is, you feed this excitation matrix to one array, B, C, D, E. Different. You can see the same. This is all +1, 0, +1, -1, +1, -1, +1, -1. So basically, you can. Why I'm giving this matrix is that there is a very good relationship between each of these matrices. You can use it in FPGA processing to easily give the excitation matrices and change them mathematically or by digital signal processing without too much of haters in them. So that's what it is. And I try to explain this slide how the 4x4 beam switching scheme works and how you can generate those beams. Now, for the first one, you see all the +1, all the +1, everything is +1 here. And how I look at this is, I propose that we look at the array in this fashion. That is, I say, look at the first 2 rows, then the next 2 rows, then the next 2 rows. For the first 2 rows, you have a beam like this. For the next 2 rows, you have a beam like this. For the next 2 rows, you have a beam like this. They add up, you give this beam, and you get this beam. So you get the both side beam. For the next case, the first 2 rows are plus plus, third row is minus, fourth row is minus. So the first 2 rows are plus plus, you get a beam like this. Second and the third row is plus and minus, so you get a split beam as I discussed before. And the third and the fourth row are minus, so you get a beam like this. And this beam enhanced by this beam enhanced by this gives you 2 beams with higher amplitudes, which is this. Similar fashion you can see here, but there's a cancellation effect because of the opposite vector orientation of these excitations, and you get a cancellation here, but the beam has changed its direction, you can see, because of the cancellation, enhanced cancellation. Similarly, you can apply the same concept for this grating lobes. If you make a grating lobes, it's not a grating lobe, it's usable lobes. To make these as 0 in the center, then this becomes 4 lobes. You can generate 4 lobes. You can also get a slant configuration using that. Now this is what I'm trying to say using this is that if you have a predefined direction in the space where you want to get your beams, and you don't want to be scanning all the time, and you want to switch your beams at particular times, then I think this is the way to go forward. And then what Massimino antenna array is, this is the antenna array that was simulated, the model of that, the simulated 4x4 antenna array S parameters, 13.5 to 14.5, 10 dB return loss, port-to-port isolation is this, you have minus 25 dB line, everything is better than minus 25, and the percentage radiation efficiency simulated is 97.5. And then these are the measured results. I can show you the comparison right here. I just didn't put them together because it was too crowded there. So measured and the simulated also it is 13.5 to 14.5, so it has a good behavior there. And this is the measured worst case visual coupling. It's a bit difficult. It's a minus 25 dB, this line here. I have a table here which I put here. So it's measured visual coupling at 40 GHz. For all the cases between the elements, the mutual coupling is much better than minus 25 dB. Okay, I was talking about phases all this time, so I just said phase, feed the phase, but how do you feed those phases? It's this. So this is a feeding network that is there for the antenna array. It uses a classical, this is the classical corporate feed you might have seen. There is nothing different in that, it's just the classical corporate feed. What is the feeding point is this, and there are each of these points are where the antenna are connected. 16 antennas are connected. This is the classical corporate feed, but to feed the 180-degree phases, this small twist was given here, a U-bend, so that all of this becomes 180 and this becomes 0. So you have two phases in the same design. I would say this was a good approach to realize the phasing network using the same antenna, using the same feeding networks. And this is the difference between the phases. Ports 9 to 16 and ports 1 to 8 is 180 degree. It's clearly the phase shift is there between these ports. That is one method of realizing it. The other method is you can have hybrids, 180 degree hybrids, feed the difference port 0, 180 and get the 0, 180 outputs and then connect it to the antenna, or you can, before that you can put a power divider at 14 GHz. And then this is the fabricated prototype of the antenna array, front view and the back view. This is the antenna array feed with the feed network. This is the feed network, and this is the feeding point. This is the antenna array. So you have the cables well far off, and this is the supporting structure, and this is the measurement setup in the anechoic chamber. And this is a PTI, the anechoic chamber. Massimino 2 beams along the elevation at 14 GHz, and this is the measured pattern of the antenna array. This is like you have the measured pattern, and this is the 2 beams along elevation 2. This is first beam, this is very close, and these are outside. These are much towards the obtuse angles. So this is 4 beam, it has been validated. So what I am trying to say to this slide is, if you have this structure and you close these 2 beams, you have this, that is what is here, and this 2, closing these 2 is what you have here, and all these 4 beams are what you have here. So this was not just a simulation concept, it has been validated by measurements, confirmed by measurements, that you can get these multiple beams by just switching between the elements using only 2 phases. You don't need to make any other phase states at all, only 2 phases, 0 or 180 degree. You can control the entire antenna array pattern with some limitation, of course. Yeah, there are some trade-offs. I mean, this is usually useful in situations where continuous change or dynamicity is not required. I mean, such cases you can. And also, if the switching is good, if the switching switches that are used are very good, then of course you can use it for even the scanning purposes in that case. So simulation versus measured pattern of the antenna array. This is just to show that there was a good agreement between the simulation and the measurement. Those ripples are because of the reflections, and the reflections took an upper hand over the actual measurements. So therefore, those are the reflections. But the idea was not. The focus was not that. The focus was to see that there were 4 beams that were formed in the measurement. That was the focus was on. So this is the reflections again there. These are, you can see they are more prominent along those structures around after 30 degrees. This is the Bose gain around 18 dBi gain, as you can see here, and 18 dBi gain at 14 gigahertz. The entire antenna operates at 14 gigahertz. The antenna array operates at 14 gigahertz with a spacing of with a bandwidth of 1.5 gigahertz. It has a good cross-polar discrimination for the entire band, as you can see here for the Bose case and for the 4B case. Of course, there are some deviations, but those can be explained. Yeah. Single RF MIMO antenna array. Okay, so that concludes my discussion on the massive MIMO antenna array and its applications and the design. Next, I go to what is called single RF MIMO or the spatial modulation. Generally, when you have massive MIMO antenna arrays, okay, so the idea is that you feed each of the antenna element with RF chains. You put RF chain. If there are 100 antennas, you put 100 RF chains. If there are 1,000 antennas, you put 1,000 RF. That takes up a lot of power. So the idea is to have a single RF. As the name suggests, it is single RF. The idea is to have only one RF chain, and that takes care of all the beam with the same beam pattern of that at least tries to come close to what the massive MIMO antenna with all the RF chain provides. So there are 3 ways of realizing this. There is SPAR, there is beam space MIMO, and there is spatial modulation. These are all 3 well-known concepts. It's been there for a long time, and I'll just give you the brief features of each of them. SPAR is electronically scanned parasitic antenna array, where the central active element is actively fed and the surrounding elements are passive, and you just cycle the beam. And in beam space MIMO, you form mirror image patterns, and you map the symbols onto those mirror image patterns and just switch between them in a very quick fashion by using an XOR gate, so that using only one antenna pattern, you can send 2 symbols. So actually you are doubling the bandwidth by using beam space MIMO. In spatial modulation, additional information is encoded over the position of the antenna along the array. That is, if you have 100 antennas and you say this antenna at this position has sent this message, then you are sending extra information. You are not only saying I'm sending this message, you are also saying from where you are sending that message. So when you do that, for the receiver, because it has channel set information beforehand, it becomes easier to match and decode the signal because it has that information a priori. So that is the advantage of doing spatial modulation using antennas. So for this, I propose this kind of a single RF MIMO 3x3 antenna array. You might ask me, why is this structure the same as the one that was in massive MIMO? The whole idea is that to use the single RF concept into the massive MIMO array directly, so that they both work hand in hand together. Single RF MIMO and massive MIMO array together. How do you do that? You have, okay, this is the return loss. It's well matched, 13.5 to 14.5, and this is the beam patterns for that, and these are the simulated beams. So this is the, I'll talk about these in more detail in the next slide. Yeah. So basically what I do is, you have a 3x3 antenna array here. This is the central one, and this is this, let's call this port 5, and this is port 2. So between port 5 and port 2, you put 0 and 180. And then you match the subnet address. Then between this, you put 0 and 180, match the subnet address. When you go like this cyclically, you get this kind of a beam function, and this gives you 8 rotating patterns, which can be obtained. I'll just give you an animation of that. So you take these 4 elements. I'm showing you this because that was for 3x3. This is for 3x3, and this is for 4x4. So independent of you use 3x3 or 4x4 or any number of, it is scalable in space and also in in space and also in frequency, up to the limit to which the antenna can provide it. So what I'm trying to say is that, without saying, I'm just trying to say you can just pick up subarrays from a big massive MIMO array in numbers which you want, in matrices, in square matrices which you want, and still implement this single RF MIMO concept. So in this 4x4, you feed these 4 with plus, these 4 with minus. That is, these are 0 degree phase, these are 180 degree phase. You get a beam like this. Then you feed these 4 with plus and these 4 with minus. You get a beam like this. Then this and this. As you can see already, the beams are a direct function of the way in which you orient your vectors from this. So it's a way of controlling the beams in the spatial domain. So this is all the beams put together in the 4x4 antenna array, and this is for in case you want to implement it in 9x9. There is a 9x9 antenna array here, and you have these subarrays with all of those antenna patterns. This is also useful in what is called index modulation. That is, you can have a subarray. I can say, if I send message from this antenna, I can say I'm sending message from this antenna, I'm sending this message from this antenna, also from this subarray. So I'm giving even more information by a single transmission. So that's even more implicitness already embedded in the message, which makes the amount of data overload on this network much lesser. That's the idea of that. So this is the measured pattern and gain of the SRF MIMO antenna. There's a good agreement between the simulated and the measured for the rotate 1 pattern and the rotate 4 pattern. And these are the gain versus frequency patterns for the 2 antennas for rotate 1 and rotate 4. But I have only put 1 and 4 here. All the 5 are measured, and only for brevity purposes I have not shown it here. So the main thing to be noticed here is that the dual beam character is here. This beam is different, this beam is these 2 beams, and there's a null in the center, and it has a low cross polarization along the higher peaks. Along the higher peaks there's a low cross polarization. And it has a gain of 9 dBi, and that's okay because SRF, single RF MIMO is a moderate traffic application. It doesn't require high gain. It usually requires moderate gain of antennas. Okay. This is the last antenna that I proposed, that is the millimeter wave antenna. Okay, in millimeter wave I said that there is the main thing to be addressed is the path loss. The path loss is very high in the millimeter wave frequencies. So for that you need high directivity beams. So the problem is that to make this high directivity beams, there are multiple approaches. This approach seemed fascinating because it uses a lens and it converts the cylindrical wavefront to planar wavefront. That's how the gain enhancement happens. So basically what you're doing is you're feeding the antennas and you're converting the planar here. So this is the antenna structure, and these are the different current distributions for surface current distributions for the central port excited, the extreme right port and the extreme left port excited for a 3-port antenna. So this is the planar wavefront you can see here. You can see planar wavefront, you can see planar wavefront, cylindrical, cylindrical and cylindrical. So just to show you what happens if you don't use a lens and what happens if you do use a lens. I have done 2 simulations, two setups here. One is without a lens, you can see the beam is much wider, there is no focusing there. And one is with the lens, the beam is much focused. And these side lobes are because of the diffracted field radiation outside the main lobe. And this is the structure I will talk to you about in a few seconds. This is just the phase distribution inside this structure, and how it is, what is happening here, I'll discuss with you in a few minutes. Okay. Let me take you through the design steps of this antenna. For this antenna, the main consideration was to design the parallel plate waveguide right. That the separation between the parallel plate waveguide had to be got right, because that controls the excitation of the higher order modes. If you don't excite the parallel plate waveguide properly, there may be other modes which may be existent, which may give some unwanted radiation. So for that purpose, the first idea was to make the parallel plate correct design. So the separation for that from this well-known equation was for cutoff frequencies about 20 gigahertz. was derived as 7.5 mm. So with the parallel plate separation setup for the design, that is this, the parallel plate separation is this. In this antenna design, this is the parallel plate and this is the separation between them. These are the three horns, this is the ridge, this is the lens, this is the flaring element. So these are the things, and if you have that, if you have this parallel plate separation of 7.5 mm decided, the next is to decide the feeding horns from that. So the mouth of the feeding horns were made in such a way that they had the same aperture height as that of the parallel plate waveguide, so that they just match into the parallel plate waveguide, and there is a good matching between them. And then this was made to have a E-plane sectoral horn, and this was a 15 mm by 7.5 mm dimension, and there was a good input matching between the sectoral horn and the at those frequencies, 28 GHz and 31 GHz. Now this antenna was operating in two bands, that is dual band operation. One is around 28 GHz and another one is at 31 GHz. This is basically because this has an application in LMDS, which I will talk about in the next slides. I will talk about that. The outer horns are tilted towards the center to target the design angle of 60 degrees later. Okay, now after discussing the parallel plate waveguide, the feeding horns, I'm going to go to the actual control part of the design, that is the ridge based lens. First, let's look at the location and length. How do you set that? Now this is the top view of the E-plane sectoral horn that we saw. So for our purposes, let's focus on a single port right now. So this is the first single port, and this has a top E-plane sectoral horn. It gives you a beam like this. What you do is you pick up the minus 12 dB point on the beam, that is here, and you see the beam width at that particular point, and that is 66 degrees. And then you project enough distance from 66 for a 66 degree beam, which is equal to the Fraunhofer distance, far field distance at 28 GHz, using this trigonometric identity, and then you come to a conclusion about the length of the lens, that is this, which is 57 mm for 28 GHz. And this is the parallel plate waveguide bottom plate, and above this a top plate will go, which is also of the same dimension. So that's the configuration here for the location and the length. The location is 50 mm from the feeding horn, the length is 57 mm of the ridge base lens. So it goes here, the ridge lens just goes there. Okay, so we got the location, we got the length. What about the height? What does the ridge do? Why do you need a ridge lens at all? Now I said in the millimeter wave antenna, you convert the cylindrical phase front into a planar wavefront. So to do this conversion, you use a transmission line. And how do you use this transmission line? In this case, we use a ridge-based transmission line, and that's the lens actually, which corrects for the phases. So it's like a tapering, it's like a U-shaped bend which corrects for the phases. But how much should it bend? How high should it bend? That is answered here. So this is what is the height. This is what I discussed before. You have a distance like that, you get the ridge-less lens location there. Now, this is the cylindrical wavefront. 0 dB, first plane, second plane, third plane. Cylindrical wave, as soon as it impinges the ridge-based lens, it becomes planar wavefront. It just goes like this. So it becomes something like, you have two phases here. What I'm trying to say is that you can pick up the points A and point B from this phase distribution of this parallel plate. On the parallel plate waveguide, you can pick up these two phases and find what is the difference between the phase at this point and this point, and from that derive the height of the ridge that is required as a correction towards that. So what you do is you set this height equal this entire length will be the correction that is applied for the phase to go from here to here, so that it becomes a planar waveform. So this is the red path length, that is the phase difference between the phases here, spread over the phase gradient over the parallel plate waveguide. And I have to make an important note here, that is, this is the phase here and this is the phase here. We took two extreme points and this is an averaging. So this cannot produce the same effect as you would have tapered the ridge lens or tapered the height, but this actually simplifies the fabrication process. But the concept is still validated. That is the concept. Yeah. And then after the lens is made, the flare radiating aperture, that is given in front of the lens, is given a 1 to 2 dBi of flare is given. Right? The flare gives additional 1 to 2 dBi of gain, and this is because of when you make the flaring, you see to it that there is no quadratic distribution of phases at all. Everything should be linear. That is, you make sure, but you cannot go beyond the limit, because if you go anything more than that, the flat phase becomes quadratic and there is a dip in the gain. So keeping these two considerations, the flaring angle is set, and you arrive at around 1 to 2 dB of gain using the antenna lens. But it's very clear. I have slides to show that there is no confusion between the gain obtained between the flaring angle or between the lens. I have slides which clearly demarcate the gain obtained due to the flaring angle, the gain obtained due to the lens, when the lens is there and when the gain flaring angle is just there. So they are independent of that. When you do that, you have this kind of distribution with 3 ports, 3 beams in 60-degree directions, and this is center direction. This is the extension to the 3 ports. Okay, that was the design aspect. This is the fabricated prototype of the antenna. This is the design model. This is the center-based lens in the center, and this is the fabricated prototype. You can see these are the coax to waveguide transitions here, waveguide to waveguide transitions here, and then the entire antenna, which is completely all metal. There is no other element used. It's all metal antenna. This was measured in the network analyzer for the return loss characteristics. The S11, S22, S33 characteristics. You can see there is a good match for 28 GHz and 31 GHz for both the cases, S22 and S33. But at S11, you see that there is a small indentation here that can be attributed because to connect to this central antenna, this cable, you have to take an elbow connector right here. So that elbow connector makes this kind of a dent there. Otherwise, all the 3 return losses are well matched, as expected in the kind of a horn antenna. So this is the port-to-port isolation, S12 and S13, well below around 20 dB there. You can see from the measured and the simulated. Measured and the simulated patterns compared here for port 1, port 2 and port 3. So at 28 GHz that you can see here, there is, if you look at these patterns, you can see there's a good agreement between the pattern shape, but there are a few side lobes that are seen here. This one here, but these can be attributed to the side ridge, the additional 3-port configuration that is there. It comes because of that. But this can be also called as the shoulder lobe, which may be useful at certain times. So gain and XPD versus frequency is this, and this is the gain that is around 18 dBi, and here it is 31 is also 18 dBi, well around 20 dBi gain that is required from millimeter wave antennas. Cross polar discrimination is around, as you can see, 25 dB, more than 25 dB for both the cables. Same thing happens for 31 GHz. The patterns are more a little bit well behaved compared to 28. I mean, the design is both for 28 and 31. So that is the case, and this is the gain pattern reflected gain and XPD characteristic. Gain is around 18 dB and XPD is 25 dB difference. Okay, so I want to say that to conclude, I want to say that for addressing 5G problems, 3 antenna designs were proposed, and each of these 3 antenna designs had a theoretical background to it, a way of approaching towards the solution. And this was not just by simulation, it was experimentally validated, and the experimental results agreed well with them. And this was true for all the 3 cases of massive MIMO, where multi-beam switching was done with a novel multi-beam switching scheme was validated. For single RF MIMO, where a mirrored beam pattern was validated by formation of orthogonal basis functions, and for a millimeter wave dual band antenna, where dual band was validated along with simultaneous multiple beams that can be projected through the lens. This is what I can say is a conclusion to my work. I would like to say that over time I have been involved also in disseminating the research I have been carrying out in different portals and foliums. So this is what I have done. I have this is the international symposiums I have taken part in, ISWCS in Bologna and in WSA Bonn, Germany. And 3 journals. I've submitted all the 3 journals. One is under revision now, the IEEE transactions one, and the other 2 are submitted to the Springer, EuroSIP, and are awaiting the review. This is this. And I've also been giving public talks at different places. Those 3 public talks each year. I also took part in the European Researcher Night. Those are my friends in 5G Wireless ITN. It's been giving. Okay, that's. And this is the YouTube channel that where I have disseminated most of the research work that I've carried out. So this is the. Okay, the future. What is next? So all of these antennas can be put into ultra dense networks, 5G ultra dense networks. Performance validation need to be done. I've already done it, but still ongoing. So that's a future extension to this. But this will be very useful to test such kind of antennas in 5G small cell scenarios, especially in crowded environments or in small areas, like probably in like a room like this, or where you have multiple pico cells inside the room, or access points acting as base stations, which is what we are going to see in the future. So in such cases, antennas will need a complete revamp in the way they are going to be assessed. Not only in the way they are going to be assessed, but also the antennas themselves need to be revamped in their design as well. So both the things need to go hand in hand. So this is what I foresee as a future extension of this work. I'm very grateful to the 5G Wireless project. It's a European Horizon 2020 project for having funded this project so that I could carry out the research. Thank you very much. This is me. That's my contact.
Thank you very much for the presentation. Now we are going to start with the questions.
First of all, congratulations. It's a huge work, with simulation, fabrication. You have built, fabricated all the structures, measured, agree with the simulation. So it's a huge work, and 3 different environments, 3 different kind of antennas. So it's a good work for your PhD thesis. So said that, I have different questions from reading the document. So I start, and when you get bored, you cut me. I continue next. Well, some questions. You say in the document, in the first part of state of the art, you talk about experimental results show that high frequencies are not that harmful for cellular communications. You assess that, but you don't say where do you get that asseveration. How you say, where do you get that experimental results? Where are these experimental results? So, which is the origin of that high frequencies are not that harmful for cellular communications? And you don't say, you don't write any reference to say that high frequencies are not so difficult for that.
Okay, Michael. So if you would let me, I would just like to say that when I say high frequencies, I just meant about frequencies which are not, of course, about gamma or X or all of them, but only cellular communications. But I completely agree with you that at very high frequencies it can be harmful. But my focus was when I wrote that was that as a general concept, there are 2 groups in this discussion is on. Some say it is dangerous at very high frequencies, some say it's not dangerous. But I would like to identify myself with a group which says it is not dangerous. So I think it is not dangerous, and I think there are multiple number of references. I'm sorry it was not included there, but if you would want, I would share with you later, which tell that in fact, there are committees which have been set up to assess this. So say clearly that it is not harmful at these frequencies, at especially these frequencies or that we are operating on. So there are some people who say that it's harmful, and for the only thing is that they say 5G is something very harmful. It's full of out of high frequencies, and it's not. That's not the case. It's not that harmful at all. Because if you look at the actual physics behind it, it's just the wavelength. The wavelength at which the 5G operates does not ionize your cells. So there is no ionization that happens in your cells. So it is definitely not harmful at that frequency wavelength, at least to the frequencies of 110 gigahertz. I mean, people are also bringing in terahertz into 5G now. So even that is okay, I guess. Unless, of course, we don't use gamma or X-rays or any other higher frequencies. Until that, I would say it is still safe to use these frequencies.
Because I'm working in making measurement campaigns and that frequencies, so it was strange for me that you don't mention any study about propagation characteristics in microwave. So I agree with you that the results of measurement campaigns are with this what you say, but you don't put any reference, so that's why I want to know. Well, it's a question I have. I don't know is a typo or you have said what you want. Talking about circular polarization, the gain of an antenna, you put a gain of 18 dBIC. I don't know if you want to say that.
Circular.
Circular or
circular. dBIC circular.
Circular. I have a problem about that notation of dBs because the standard definition of gain is using both polarizations. So noting circular is a redundance. It's, if you talk about dBi, dBi is both polarization. Usually you have linear polarization and you use a probe with linear polarization. But if you are measuring a circular antenna, the gain is using both polarizations. So it's strange for me to see that notation, and the IEEE standard of measuring antenna says exactly that the gain is with both polarizations. So the first time I say that notation, I investigate that some authors talk about that, but I think it's a redundance. It's not stated in the standard of that. So I want to tell you that you to be aware of that kind of.
I take note.
All right. Something about the notation also. You talk about the electric constant, but I think you want to say relative permittivity. The electric constant is epsilon 0. It's a constant. Epsilon 0 is the constant. So the electric constant, epsilon 0, relative permittivity, epsilon r. So it's another concept that maybe in most papers there are this misunderstanding or changing words, but I say it in my classes at the school. So it's I say in paper that there is this use of the words, but the constant is the constant, and the other is relative permittivity. All right. you talk about, you have used, of course, a simulator to make all your work, but I haven't said nothing about what kind of simulator you have used.
Okay.
Is your own program? Is any commercial program?
Okay,
I don't know
I will-
what kind of simulator you have used.
I have used two simulators. Both of them are FDTD based, finite difference time domain based. One is HFSS, the other is CST. And both are based on leapfrog scheme. They discretize the cells. They make the entire cell and discretize the entire boundary, and take the small E cells and process the fields inside each cell and solve for it. So I've used both of them, which are FDTD solvers, so that there is no. I mean, there were some things which were good in one and some things which are much better in the other one. So I used both.
I was very strange that you haven't written anywhere or in the presentations which kind of simulator you have used. So I don't
And
know
suspicion
if
was
you your own work to simulate or you have used any. All right. The matrix T of the parasitic reflector. Where it comes this matrix? It's from a paper?
Yes, it is from a very well-known paper. It's based on refractive index retrieval mechanism. It's made in 2001 or something. It's a well-known paper. So they have a clear-cut formula which they derive from the S parameter. They provide the substrate as a transfer function in itself, and the input signal and output signal, and they try to model the refractive index behavior based on that. And they come to a very nice closed form solution in which they relate the S12 and the S11 parameters for the two-port network with the refractive index, real part of the refractive index. So what I did was I adapted that into a code into the solver and extracted those parameters from my design and saw the behavior of the change in the refractive index as I proceeded towards in the design. That's what I did.
Because in this formula about the parasitic element, I only see that the D is the wide of this element, but I don't see in the formula if the angle of this element
that is
only in the formula is the D that is the width
is this. Yeah, this is this
it's
D.
the distance.
The distance, yes.
I understand it was
The arc length is this. This is the arc length. This is the arc length.
But the arc length isn't in
It's not in the formula.
in the formula. It
No.
depends.
No. Is because this completely is this entire thing, this structure, and its spatial location with respect to the port defines the behavior of this refractive index. So here it is more closer, here it is more further away. So that defines the refractive index. In fact, in the derived formula, they don't consider the
If it's wider or smaller, it doesn't depend. It's strange for me that this size isn't in the formula. I don't know.
I agree. I understand and understand your concern. I would say that if it's very big, it would be taken care by the ports that you excite. If suppose this is bigger, the ports that you excite will take care of that. I mean, this essentially is like only for this purpose. It's like this becomes a way of looking at it is this is longer. Then from this point to this point, and from this point to this point, there is a difference when you excite the ports. I think that is what reflects as the actual measurement of the structure here. That is, the structure is longer, then it has to have a different response than it has to have when it is shorter. So implicitly it would be included in the port measurements of the antenna. But this kind of a behavior is assessed for coupling the fields from this point to this point to this point to this point. I am not sure if I am clear for you. That's what I think. I mean, on the outset, if I understand your question properly, that is what I would say. But I do agree that this would depend on the size, because of course it does depend on the size. But that size measurement will be taken care of because the ports that you give will also be so long. So if the size is so big, the ports also will be correspondingly so big when you measure it along it.
Oh, the radius.
The radius will be
the
yes,
is
the radius.
not in the formula, so it was strange for me. All right. I have many questions, but for the end, an ending question. In page 73, you talk about, for example, cross-polar discrimination is around 20 dB for 14 GHz, but I see the graphics and I only see 15 dB of cross polarization. So I don't know if I'm not saying the same, or it's not the right pattern if you want to have a look, or
Yeah.
but 573. This green from this, I see 15 dB, and you are saying 20 dB of cross-polar discrimination.
Okay, that's.
So I don't
No,
know.
I would say go by this. The figure is the one that is correct. This is something I might have just over. It should be 15. If this is the case, this is 15 dB, right? So if this is here, this has to be 15 dB. This is just I need to correct it to 15. That is what I would say. It's the figure that takes precedence. This is the figure is the actual.
Well,
Thank you.
thank you.
Susana?
First of all, I would like to thank you also for your presentation, which has been very clear and illustrative and short, not too long. So it was. I think you went just to the point, and you have made a good presentation. Well, I would also like to highlight that you present an extensive activity during the period of realization of the thesis, with participation in research projects, attendance at meetings and courses, etc. So, and could you please explain us the context in which the thesis was carried out? Because I understand that you weren't here at the university. Just a little bit about the context of realization of the thesis.
So I came across. I was looking for 5G based antenna design work, and there was one opening here in TTI, which I came across. So that was why I joined TTI, and I work in TTI, but I had to after my work there. The context was that I was researching in the 5G wireless horizontal pretty ITN for almost a year and then I had to. I thought my work can be taken further with a PhD, so that's when I thought I will start with my PhD, and then I got in touch with Professor Jose Bastarisha, and that's how all this gets into context. But I can say it's been a very rewarding and learning experience for me.
Okay, so thank you. Well, as you say several times around the document, Well, I understand that the work is more a proposal of technologies and demonstration of its viability than final prototypes. Well, that's what I understand, because there are, so regarding the technology, have you considered or evaluated the possibility of using, for instance, for the massive MIMO and the single RF nano, the possibility of using transmitter arrays in order to avoid the 3D network? If you have considered, and
Yeah.
pros and
Yeah, actually,
advantages and disadvantages
yeah,
of
actually-
each other?
yeah, okay. So the transmitter arrays, the thing is that it's really a very good thing because there is no you don't have to use a parabolic reflector, or you just there are no reflections, and you just pass it through the array, and it just makes all the beams, scanning stuff, and all of those. It's very nice. Here I have not the one that I showed, that is the massive MIMO array and the single RF MIMO array. I would not relate to them as transmit arrays, but then I would relate to millimeter wave lens antenna as a transmit array. It can be viewed more there in the millimeter wave, it can be replaced by a transmit array feeding the horns. So I would relate more into that, and it would have added advantages as well. The comparison for that would be that this has already a mechanical supporting structure. The parallel plate supports the lens as well already. But in general, in transmit arrays, you need a supporting separate stuff, and that's one thing I would say. But the advantage of using a transmit array is that you can realize a 3D planar scanning. This is a uniform plane scan. This what I shared with you here is one-dimensional scan on the plane, this plane. But if you use a transmit array, you can use anything, like you can make a 2D scan completely. So transmit array gives you that freedom to do that. But if I want to extend this antenna, the millimeter wave lens antenna, to 2D planar scanning concept, it's very difficult because the ridge becomes a hinder. The ridge is always there, and you cannot place one above the other, and all of those problems come up. So in this context, transmit array is much better. That is what I have to say with transmit array and millimeter wave lens. But with transmit array and massive MIMO and single RF, of course I want to add to it as well. The arrays that I showed here, they can be used as meta cells. Instead of antenna elements, they can be used as meta surfaces or meta cells, which can be excited with the same phasing schemes, that is 0 degree or 100 degrees that we use, to create multiple beams. In fact, the antenna itself becomes a meta cell in this case. In this, what I showed here, the antenna array itself becomes a meta cell. So you can extend it to that. That's for massive MIMO. And for single RF, using transmit arrays, you can. I think it's much difficult to make it a single RF, because transmit arrays operate in union. They need to operate in groups, so you cannot isolate stuff. So it's a more challenging. It's not difficult, but it's challenging. So single RF shouldn't be done with transmit arrays, if you ask me.
Coming back to the quasi-optic element, because I don't know if I understood completely what you were discussing before. Yeah. How do you define the radius of the element? I mean, which is the difference between a more curved or a more plain arc?
Well, actually, this arc has these arcs are all having the same curvature. The radius of curvature is same for all of us, and the centers are here. It's right here, and you plot an arc.
Yes. But
So
how do you choose the center of the radius?
The radius.
Yes.
the radius of the arc.
Yes.
Okay. Well, when I show you this, there has been a lot of work that I did before getting into this this design. So.
I mean,
There
which
are
is the
certain-
influence
there are-
of the radius?
That formula is one thing. The other thing that can give you that is, you can change the radius in a way that you see what is the amount of. I can show you the surface current. This one. What I mean to say is, when you make these radius changes, the amount of surface currents you see changes as well on the arcs, for different shape of the arcs. So the arcs where the surface current distribution becomes the maximum will be the amount of curvature for which the arc is considered.
I suppose that the arcs, the number of arcs, and the separation between arcs.
The number of arcs, I can tell you, it cannot go more than 5. If it goes anything more, there is no much increase, because it becomes so parasitic that there is no energy coupled at all. So you cannot go more than 5. You cannot put 10 or 12 or something like that.
Maybe simulation.
Yeah, maybe it's by simulations
Another thing I want to add to that, if you let me, yeah. So this arc, there is a particular reason for selecting this. There is another way of doing this. Okay, you can just put here 2 square patches, and then put here a square patch, here a square patch, here a square patch. Why do you use an arc? So there is a particular reason for selecting this arc. That is, if you use this arc and if you use a square, it is well known a sphere has more exposed surface than a square. The amount of exposure that is there here through this is more than the exposure you get through this kind of a straight line. What I mean to say is that the coupling becomes much better because there is more exposure from this copper to this copper. If you make this just like this, okay, it is good, it is linear. But when you have a coupling that goes on like this, you need to have it in a spherical fashion. Just like you have these hexagonal cells, that is, it's like if you have 3 circles and you place them adjacent to each other, there's a triangular space in between them, which is the minimum surface area that exists between them. It reduces the surface area. So to put it very simply, I'm saying that this arc resonator shape is taken as a curve because it maximizes the surface of coupling to the next element. That's why it is the arc resonator.
Yes. In general, you have in the massive MIMO antenna and also in the single RF and also in the length, but well, we'll talk later about the length. Sometimes you have secondary lobe levels about 12 dBs. How can you improve? Because sometimes you have
In massive MIMO, you mean?
you have some lobes a bit high.
In
How can
massive
you
MIMO?
improve that in the?
You mean in the massive MIMO or in the?
Yes, I have here, for instance, in page 73. Yes, this is the massive MIMO. Well,
This one, you mean?
for instance, you can here you have 4 lobes and the third lobes, well, is almost 10 degrees
That's the okay.
high.
This one, right?
Yes, maybe that one, for instance.
Okay. So this.
Between the second and the third lobe, you have less than 10 degrees.
I think this is much. If you see, look at this. Okay. So this is the lobe. So it's looking at the horizon. Doesn't matter. So it's like it's here. This is the lobe that you saw there.
Yeah.
This one, right? So it's on the. It's right on the. If you have this base station or okay. One thing is you can reduce it, but I'm just trying to say that this will become not. This is not that. Its effect is not that much because this is looking into the horizon. The beams are right here, and these are looking at 180 degree and 180 degree. So if you place an antenna right here at the small cell, those are outwards that way. So that's what I mean. But if you want to reduce that, there are 2 controls that you can have. One is you need to reduce the inter-element spacing that you had. This is basically that's what I call the grating lobe. This one. In fact, what I'm trying to say is this is not a grating lobe structure, or it's not. These lobes are not coming because of the grating lobes. These are usable lobes because they are all of equal amplitude. But if you want to remove that, I think it can be removed by controlling the space. This was obtained by putting this at one angle 0, this at one angle 180, and these two are match terminated. So if you decrease that gap between them, following the aliasing effect, you can have that grating lobe reduced. This one, this one.
What is the lens results? I don't know if you have there the graphics, otherwise we can.
This one?
No, the patterns. The radiation patterns. Well, there. The secondary lobe, there,
Yeah.
near the main beam.
Yeah, this one, no?
Yes.
Yeah, this is what I refer to as the shoulder lobe. Well, actually, this is what I have spent quite a bit of amount of time trying to allocate, trying to assess what is the cause for this. So the thing is, from my understanding, I would attribute that to the difference in the length of the lens grid. If you look at this, okay, if you look at this figure here, now that is for port 2 and 3. That is this port 2 and port 3. So you see this? So it's not exactly symmetric. And also, because of this phase aberrations around this area, the current may be distributed in a way that such a kind of a shoulder lobe exists. But for this case, when this is exactly straight, there is no shoulder lobe for that case, as you could see.
But didn't you try in simulation to see it changes?
Yeah, that is what I mean. This is because for this case, you cannot increase this by simulation, this distance, because this distance is fixed. That's my limitation. I cannot increase this distance. So it has to be there, and because of that, you have this behavior.
So if and does that behavior is it worth to try to improve that behavior, or you can manage with that lobe?
No, definitely no. It's definitely possible. What I'm trying to say is that you can make that behavior. All I'm trying to say is that this is this entire length that you see here, and the length that you see here cannot. If you push this away a little bit further away, it will become more symmetric, and this will also open up completely. But for this purpose, we have seen from our previous slide that this length is fixed because of the Fraunhofer distance. You cannot place it anything more than that. If you do anything more than that, the function of cylindrical wavefront becoming planar wavefront will not happen at all. So you cannot move this out. So this is like a trade-off between this location, direction, and the gain, all the three. So basically, if you pull this all three out and operate at lower frequencies rather than at 28 GHz, you will have more margin to go around with the lenses. What I have done here is a piecewise approximation of the actual curved lens that you usually follow. A parabolic lens, contour lens, bifocal lens, all of these lenses follow a complete circular structure. What I have done here is a piecewise approximation, which is 3 pieces, 1, 2, 3. So this, the main condition is that the direction was 60 degrees, the gain had to be high, and it shouldn't have any kind of change in the distance between this and this.
And could you could you improve the gain of that lens? Because you talk that at millimeter waves you need very high directive antennas with gains, you said at the beginning, gains higher than 20 dBs, and you are getting around 15 dB. So
Yeah, you can.
could you,
I can put some
with
light on.
that kind of lens, could you get
Yeah, I
more,
can.
higher gain? Or?
Yeah, I can tell you why this is at 15 dB. So the thing is, this antenna, you can see here, is at 15 dBi. For this, 28 GHz and 21 GHz at 15 dBi. So the whole concept of making this antenna was to put it into LMDS, local multi-point distribution systems. So for local multi-point distribution systems, you have two frequencies, 28 GHz, 31 GHz. And they usually looked at gain bandwidth, gain dBi for that is 20 dBi in the LMDS minimum. But now, because this has a dual band operation, I said this antenna has a dual band operation. For 15 dBi itself, you can see the dual band operation. So even having 15 dBi will not give you any kind of, you see this? So this is 15 dBi. You can see this dual band operation with the lens. So for anything below 12.5, anything below 12.5, you can say the antenna is not dual band, 12.5 dB gain. But for anything above 12.5 dBi, it behaves as a dual band LMDS antenna. So it is still valid. The 20 dBi that I said is general for millimeter wave antennas. But for LMDS, it is still valid.
That reminds me of another thing about gain, and I just didn't notice this in slide 33, that I had already noticed also in the paper. That is for the single RF MIMO. Okay, when I was reading the paper and you have all the figures with the plots with the gain, and you usually say that the gain is 7 or 8 dBi, but when you see the curve of the gain as a function of the frequency, in the band between 13.5, which is the beginning of the band, you have very low gains. I mean, the gain is not very stable in the frequency band, but it has a certain variation in the band, and also it's quite small. Usually, well, at least that curve at the left is quite smaller at the beginning of the frequency band.
Yeah, I would attribute that to the frequency limitation of the network, phase splitting network. The phase splitting network that I used was made for explicitly from this 13.5 to 14.5. No, this is 14. Okay, the phase splitting network was from 13.5 to 15. Totally, it was made for N-type frequency. But the thing is that when you use such kind of phase shifters, there can be a problem of each element having a different behavior because of the limitation in the bandwidth operation of the phase shifter network which I use. So if I use a TTD here, a 2-time delay, then probably I can have a higher gain at a larger bandwidth for a broadband operation. But since I used a phase shifter which was based on microstrip, it probably is having, that's the reason I guess, in the lower bands. Maybe the bandwidth is not higher, much higher, that's why. 2-time delay line may have, I'm not sure about that, but I just used it because it was much more cost effective and it's easier for me to verify it.
And just a last question. In the lens antenna, which capacity do you have? I mean, if you had some constraints for your radiation pattern, certain secondary lobe levels or a certain beam width, which capacity do you have in the design of your lens to achieve some constraints? I mean, if I tell you I want a certain beam width, can you control that with the design of your lens? Or you just design the lens and then
Beam width,
let's see
control
what
the beam
happens
width.
with the radiation pattern?
Control the beam width.
Yes, can you control, for instance, I mean,
No, but with
no, but I mean, when you design the lens, can you control some parameter of the design so that you can achieve a given beam width?
yeah, definitely. If you make the lens more broader and the lens is longer, it will focus more. That's the thing. But it will not definitely give you the pattern synthesis approach. That you cannot go from make a beam and then design lens like that. Probably, if you have to control the beam width to that precision, then it's only. I think there is a limit to which the ridge lens can have a beam width, because you can go, let's say, 10 degrees. I think this was 10 to 20 degrees. That's it. So you can. There is much more. If you have to attain much more, then. Okay, if you talk about a single port, then okay. It's just the
something like a, well, it's called, say, synthesis or something like that.
yeah, it's reverse.
I want to obtain this and which control do I have on the parameters of the lens to achieve the given characteristics on the radiation pattern, let's say secondary log levels or beam width.
No, just give me a minute. Just give me a minute. I'm just.
Okay.
I think the thing is that if you use only a single port, okay, single port. So if you don't use multiple ports, then there can be a method. But the moment you use multiple ports, I think it becomes a very complex optimization problem, and it may not converge at all because it's a big lens and you have grid lenses all over. So for the single lens port, for just a single lens, the only thing that can control the amount, how you control the high gain obtained, is by the way in which you correct the shape of the lens. That is, if the shape of the lens is this particular fashion, or the length of the lens is in a particular fashion. Essentially, what you are trying to do is you are just looking at one thing. There is a cylindrical wavefront, there is a planar wavefront. How do you attain this transformation? That's all. So you use a lens to attain it, or you use a transmit array, or you use a metacell, or a surface, different concepts. But the approach is the same. But in case of a lens, it becomes difficult because in this particular lens, it becomes difficult because it has a multiple variable approach. So the only thing that controls it is the lens shape, of the lens, and the length that is there. But that in itself is not enough to give us complete handle over the entire beam width, because there will be multiple parameters around spillover effect and all of those which are around it. So it's.
Okay, thank you.
Thank you very much. Thank you for the presentation. First of all, I want to congratulate your supervisor for the work you have done, and also your supervisors at DTI. In my opinion, it's a good work. I missed something because you have presented different kind of antennas, and I can't be here any prototype. I don't know why, because I'd like to see them here.
Sorry.
In order to be able to see how they are being made up and to see the size, the materials, and so on. So I don't know if there is a confidentiality with TTI and that is the reason they are not here.
No, it was my mistake. I didn't get it here.
I think it would be, in my opinion, it would be nice to have them here to be able to work.
I
with
think
them
I have a
and
video
to
of it. I can show you the video.
I like the prototypes here in order to be able to know how they were built and in order to
I
touch them.
completely.
So I have some questions regarding to the manuscript. First one is you designed for the first one for the massive MIMO. You have defined an array with elements, and you have defined the dipole, and then you have to build the reflector and the director. Did you try another kind of reflector? I mean, similar to the ones that you can see in some Yagi antennas in which they are using some diedral structure, instead of using just a straight one, use something similar to the lens you use as parasitic, something similar in the reflector. I don't know if it has sense or not.
Yeah, the only concern with that was the reflector has its very this behavior is very sensitive. The behavior of the reflector with the return loss characteristics is very sensitive. So, yeah, what I mean to say is that if I take this as if I use something like this, a reflector like that, then it will couple with this. So it's a bit sensitive. So the sensitivity is not that much. So I have to keep the reflector much away from that as well. Still retain the resonance, but still reflector should operate as a reflector. That is, it should put back those elements.
I have another question regarding the way you have simulated the arcs. I can see here 2 ports, but in which way do you feed the ports? Because it's not a waveguide port, because I can see here, if it were a microstrip, I can see the line and I can see the microstrip port, but here, how do you feed the structure?
That was a waveguide port.
This is a waveguide port,
Yeah.
and this is
That's a
ground
substrate.
plane or
Yeah.
something
That's
like
the
that?
substrate. That's the substrate. And
because
yeah.
in the other part of the structure,
Yeah.
there isn't any ground plane or something like that.
yeah, on the other side there is no. Only there is a substrate. There is a substrate here, and there is just a metal that arc on the top, and a port here on the substrate, and a port impinging on the other side of the substrate.
And which kind of waveguide is this? Because I'm thinking on a waveguide, a usual waveguide, or something,
It's
a
a usual-
microstrip, or
It's a usual waveguide, like a hollow rectangular waveguide, but it's not hollow. It's like it's not a waveguide.
In the this is the substrate of the structure. Here there isn't any ground plane, and here just the patch.
And the incidence is not from the bottom to the top, is on the.
Yes, I understand that. I can see the waveguide mode excited here in my head. I can see it if you have a ground plane and here a line. I can see the lines for the electric field, but in this structure I can see it. I suppose it's my fault. I am not used to work with this kind of structures.
I think what for that.
I think this uses boundary absorbing magnetic bond periodic magnetic boundaries in the sides and absorbing boundary conditions in the
The boundary.
slightly
I have another question regarding the directors. Will you get the same behavior using just one continuous structure similar to an open horn? You need to put different arcs. It's impossible to get the same behavior.
If you make it, yes. If you make it, I mean, I know this because that's what makes parasitics what they are. They have been used to increase the bandwidth of an antenna. They have been used to increase the gain of the antenna. But the moment you make it continuous, it's a different ballgame altogether. So it's like
It doesn't
it
work.
doesn't work.
While I was reading it, and you talk about the asymmetry, I said, why, if you are putting one arm here and the other in the other side, why don't you put? But at the end, as I was going on the manuscript, I see you have put it on the other side. I have another question. In page 47, you plot the simulated radiation pattern and then the measured radiation pattern. And here you have a bad agreement, but here in this case you have a better agreement in one plane with respect to the other. Do you know why? I don't know if it's the effect of the positioner, the rotation of the positioner.
Yes, backplate and the positioner. There was a backplate behind the antenna and the positioner as well. So the positioner and the backplate metal makes the back lobe much lesser. So that's why you see the lesser backload there.
Regarding to the prototype, I suppose you have some tolerance when you machine the structure. Did you perform some kind of tolerance analysis in order to be able how the simulations will deviate
Sensitivity
when they are so
sensitivity
sensitive?
analysis. Yes, I have done
Did you
that.
perform
I have put it in the thesis as well. Yeah, sensitivity analysis. I guess it's
not just I don't mean how the length of the dipole affect the behavior.
mhm,
What I mean is once you have get to a good solution
mhm.
and you know that when you send it to the workshop they are going to build the element with 20 microns.
Okay, that
That
was
is what I mean.
0.15. That was 0.15 when the milk was milled. Yeah, that was the tolerance limit.
Did you do this analysis in order to check that?
Yeah, most of the, in fact, this gap that you see here is also dependent on that. If I give it anything lesser than this, it cannot be milled inside that. So this small gap, it was 0.2 mm to be precise, and this gap between this has to be greater than 0.2 mm at least. Otherwise, you cannot take the milling pin inside the. So it was a consideration.
In different radiation patterns, you took in your simulations, compare with the measurements, present a lot of ripples. You said they are due to reflections in the anechoic chamber, but you are measuring at 14 gigahertz, and I suppose the size of the absorbers is high enough in order to get a reflectivity around 50 dBs. So I can't see why you get.
The power excitation was not taking precedence over the reflections.
But I can see why you get these ripples in the radiation pattern, because I think I read around the manuscript you think the ripples are due to reflections, I suppose in the walls and in the floor of the anechoic chamber. But at this frequency, I mean, if you were measuring at 1 gigahertz, maybe the size of the absorber is not enough in order to present a good reflectivity. But I think at 14 gigahertz, I don't know the size of the absorbing material, but I suppose it's high enough in order to get a reflectivity around 45-50 dB. So, and in some cases, you have deep ripples. So I don't know what is the reason.
I think that's, as if you see that diagram, at 30 degrees, after 30 degrees there are ripples for both the cases. For plus 30 and minus 30, beyond that there are ripples. So it's also a matter of.
In some cases, you are also ripples in the maximum of the beam. I don't know.
Okay.
Here you have some ripples. This is the noon, and you have some ripples in between the noon and 10.
I have an explanation for these
ones.
ones. Yeah, because I attribute that basically because if you look at this anechoic chamber setup that was measured here, I'll just show you this one. There is also this orientation also, the orientation of this form, the reflector, this absorber also affects the angle of this, the angle in which this is placed is also affecting the measurement data made.
Did you try to remove the absorber, this absorber, and to put another
No,
one?
because
Instead
there used to be more reflections otherwise, because there's a complete position below that. So it would, if I remove that, there would be more reflections.
And in this time, I don't know, this is the anechoic chamber.
Yeah.
And this is in this case you are measuring in a spherical system or in compact range?
Spherical. This is spherical.
Spherical system.
Yes. The spherical is on this side, and behind is the compact range that is here.
For me, the ripples are high enough, in my opinion. I think you can do something to manage with the ripples. Or you should do something in order to get a better
The deliberation has decided
to give you the mark of sobresaliente, the highest mark. So, congratulations.
Oh my God! Thank you.
Congratulations.
Congratulations.
Thank you so much.
You have to wait for the next mark because it has to be the envelope has to be opened in the committee, and then they inform you on your mark, on your if you have the extra mark. Okay. Okay.
Congratulations.
So much. Thank you.
And now you have to sign these 3 documents. It's for the titulation, you have to sign here, sign and your name.
With, if possible, capitals.
Eso sobra, porque ya los tenemos cubiertos, sí. No,
Es que no
están
nos
en
enviaron
blanco.
siquiera, no nos habían
No,
enviado.
son esos, te piden
¿Están
los
en
datos
blanco o no hay
de,
Here,
los datos de la
only
cuenta
the
corriente,
sign.
¿Sabes? ¿Sabes? Pues el despacho.
los
Y
precios
no,
de
está muy
pago.
cerquita,
Yo creo
¿eh?
que más o menos me orientaría.
¿Sabes? La
Sí,
Rafa.
sí, sí.
Bueno, no,